I also want to apologize to my good friend and distinguished colleague, Craig Stair. He wanted me to do a song and dance as part of this, and I was going to do the Super Chicken theme song, but the marketing representatives from Hewlett-Packard thought that showed a certain amount of disrespect, and so I'm not going to do it. Sorry, Craig, maybe tonight later I'll do that. Disclaimer, this all could be made up, but it's not, but need to disclaim things. DXC stands for Data Exacel, and it is a project that we're undertaking as part of the National Science Foundation's Data Infrastructure Building Blocks program. And the grant number is listed here. The initial funding for the grant was $7.6 million, and then we got a supplement of $1.2 million recently. And it is a pilot project. It is not a production system, and its purpose is, as it says here, to create, deploy, and test software and hardware specifically for data analytics and data-intensive scientific research. It's based on our Data Supercell, which I'll describe briefly. Sherlock is our Cray Yark Data Eureka system. Blacklight is our venerable UV1000 system with 2 partitions of 16 terabytes each of shared memory. We have lots of pilot applications, and it's, again, working towards diversity, new communities. The Data Supercell, very quickly, is our all-disk archive. We've had it in production for about 3.5 years, and working very well. It's about 4 petabytes, but we replaced our tape archive with the Data Supercell. The pilot applications are, this is the basis of this project, is pilot applications to motivate the building blocks, to test them, demonstrate them, and to improve them. The pilot applications were chosen through this to advance research in the 3 V's of big data: novel approaches to data management, novel approaches to data integration, integration of data analytic components into workflows, and complementarity to existing applications. We don't want to have duplication, but we want to complement them. For each project, there will be a PSC specialist working with them. The initial 3 projects are the Pittsburgh Genome Resource Repository, the Galaxy Program Workflow Framework, and the National Radio Astronomy Observatory. Since it started, we've added 16 pilot applications. It says that we've found additional distinct opportunities to gain experience, preparing for bridges, which is the most of this presentation, and the real thing is intense community interest when the people in our pilot projects spread the word. There were lots of other people who were very interested in working with us on this. There's a list of the 16 pilot applications, and the point here is simply to see the diversity, the new communities that we are reaching out to. There's very little traditional HPC. You won't find any computational fluid dynamics or astrophysics in here. These are all very new communities who have not used high-performance computing before. I want to mention this academic title, Solving Large Sequential Two-Person Zero-Sum Games of Imperfect Information. The test vehicle for that is a computer program called Tartanian 7, not Tarkanian, Joe, if you're still here. And it is a program that plays Texas Hold'em poker. And last year, it won first prize at the computer poker competition. but that's what he's doing. And again, here are things that you don't normally see running on Energy Labs systems at Argonne. Medieval Slavic manuscripts, medieval Christian iconography, digital humanities, etc. We're, again, really going after new users. And just to summarize, we're tightly coupling the analytic engines, which is Blacklight and Sherlock, with the storage architecture that's the outgrowth of the Data Supercell. The applications are used to motivate, test, and harden. I didn't really like the word harden, so I'll use the word that I learned from Merle Giles, which was robustify. Thank you, Merle. It's a real word, I know. I looked it up. I didn't believe you. And we're creating hardware. We're not really creating hardware. We're integrating hardware, but we're creating software building blocks that will go into the Exceed resources. Okay, yes, most of them are our resources, but of today and tomorrow. Again, it's the NSF's Data Infrastructure Building Blocks program. Now, moving right along, I've taken these in the other order because this is the way they should be. I'm going to talk about bridges, a brief introduction. The materials that they took to Washington to present the 18-month review of DXC would take about 6 hours. I've just done the DXC in 5 minutes, so I hope to get through bridges in the next 14 minutes and 39 seconds. As I alluded to in Stuttgart at the User Forum 55 meeting, Pittsburgh is a city of bridges, and this program is to build bridges to new communities whom we think and they think can utilize high-performance computing. They have not used it before. The grant, $9.65 million, and the title was From Communities and Data to Workflows and Insight, and the hardware mostly will be provided by our good friends at Hewlett-Packard. It will be part of the Exceed program. It will be allocated by the normal means of Exceed processes, be integrated with the other campuses, other projects, and instruments. It's designed to meet perceived research needs. Scaling research questions beyond the laptop. One of the working titles for this program project before it got named Bridges was My Big Laptop. So we're intending to make high-performance computing as usable, as accessible to researchers as their own laptops. We're going to encourage cross-domain analyses. There will be shared data collections and analysis tools, workflows, of course, large memory applications. I'll talk more about that, optimization parameter suites, etc. The potential applications, well, I've listed the pilot projects for the Exacell program, but here are more potential applications, again, in new areas that do not traditionally use high-performance computing, understanding how the brain is connected from electron microscopy data, addressing societal issues, finding causal relationships, et cetera, et cetera. So again, the thrust is going out to new communities. The objectives, I've said it 3 times now, bring HPC to non-traditional users and allow high-performance computing to be applied effectively to big data, And bridge to campuses. This is a big deal in the National Science Foundation, is to make the Exceed resources operate seamlessly with the campus resources. And the way we're going to do that, obviously we're going to lever our experience, especially with the large shared memory machines, and we're going to leverage our large memory for interactivity and to support new applications. More about this in a second. Here are 1, 2, 3, 4, 5 features that we felt are important in a system of this kind. It's interactivity, gateways and tools for building gateways. We have database and web server nodes, high productivity programming languages, environments, and virtualization. Now, interactivity, it says, is the feature most frequently requested by non-traditional HPC communities. We all know what interactivity is about. You don't like to, in the HPC world, I've been there for a very, very long time. Batch jobs are what you do. You put it in, wait overnight, and get your output in the next morning. But the immediate feedback from interactivity is essential for exploring data analytics and testing hypotheses. And we will do this through a combination of virtualization for the lighter weight applications, and we have dedicated nodes for more demanding interactive applications. Gateways and tools, we'll have a lot of tools and we will implement popular gateways. Virtualization, some users have computational environments, and we will be able to support those, and we'll also be able to interoperate with various cloud services. And high productivity programming, we're going to have many languages that you don't typically find on high-performance computing systems, Python, R, and yes, Java. Jim Turley wrote about Java in his Silicon Insider once. Java was a hoax or a malicious prank, but I guess not anymore. We'll have a Hadoop ecosystem. We will accelerate this with GPUs. The large memory will be great for Spark, but this slide has the cartoons of the Hadoop ecosystem. Okay, down to something that I do understand is the architecture of this system. It has 3 tiers of processors, and going from right to left, we call them regular memory nodes. Each node has 128 gigabytes, so that's kind of the low end of the shared memory scale. And these, as it says, we will have GPUs on some of them for acceleration of Hadoop and other things. And as Wrangler has, we do have a DSSD D5 array of SSD on it, 96 ports. It's not as big as Dan's, but we don't have as much money as Dan has. The next one is we call them the large memory nodes, large shared memory nodes. Each of those will have 3 terabytes, and we have the ones we call very large shared memory nodes will have 12 terabytes of shared memory each. The implementation of these things, the regular memory nodes will very likely be the Hewlett-Packard Apollos with Apollo 2000s with XL 170R blades in it. The LSM nodes, large shared memory nodes, are ProLiant DL580s, and the fun one, the big one on the left, is now called the HP Integrity Superdome X with BL920 nodes. That was previously codenamed Dragonhawk, and we had a lot of fun with that name. The system components are connected with the Intel Omnipath architecture fabric. This was previously known as Storm Lake. We have a large project file system shared by all of the nodes, and then the utility nodes, the service nodes, the database nodes, web server nodes, data transfer nodes. The data transfer nodes connect to the outside world. So that's the overall structure of bridges. What might you do with these things? The very large memory nodes, examples are genomics, machine learning, graph analytics, etc. We've had from experience on Blacklight that large shared memory, like very large shared memory, is exceptionally good for genomics, especially the de novo assembly of plant genomes, which are much bigger than human genomes for various reasons. We did a wheat genome assembly of 10 gigabase pairs that required 6 terabytes of memory for many hours. The large shared memory nodes will be used for interactivity, medium spectrum memory intensive jobs, and virtualization to support the low intensity things. And the hundreds of regular memory nodes will be workflows, interactivity, Hadoop, and capacity computing. The systems will all have the latest version of the Xeon CPUs. They'll very likely start with Haswell, moving to Broadwell when it's available. It's possible that Broadwell will be available for shipment in our time frames for some of these things. The database and web server nodes, dedicated nodes, lots of good software on there. Dedicated web server nodes for distributed service-oriented architectures and high bandwidth connections. Lots of data management, what we call the project file systems, a very large shared high performance file system visible to all nodes, again connected with the Storm Lake fabric. Distributed, and we also have distributed storage. Many of the nodes have their own local disks, and then Hadoop will be accelerated with the GPUs. Another note on the Omnipath, previously Storm Lake. It's a very high bandwidth internal network. They have optimizations for MPI, and going forward, this is sort of the first step in Intel's interconnect activities, and we feel that it's important to take advantage of this early opportunity. There's a relationship between bridges and the Data Exacel. The Exacell project produces components that will feed into bridges. It will, of course, feed into other Exceed projects as well. You can look at the diagram in detail, but basically it's what I just said. For example, the Data Exacell has DL580s in it, and today we're supposed to be getting the first, let me get it right, HP Integrity Superdome, the Dragonhawk, based on the Ivy Bridge processor. The target schedule, the acquisition began in 2014, December, working on contracts, program plans, etc. We expect first deliveries for bridges in October, and we hope that some of the new technologies will be available. Early user period, late 2015, and production in January of 2016. And again, I had very little to do with this. Well, I had a little to do with it. But Michael Levine is the PI on the DXC project. Nick Nystrom is the PI on the Bridges project. And J. Ray Scott is co-PI on both of them. So I'm 2 minutes early, and I have lots of time for questions.